So as Eddie mentioned, Millicron goes under the brand name Empowered. We've been working together since the 2013-2014 timeframe. So just quickly about Millicron, as Spencer said earlier, a 135-year-old company, basically in the injection and extrusion plastic molding business. So you've got a picture of the machine here, and just a little quick understanding of that. Plastic pellets go down this hopper, go down the barrel in a screw, as Stefan was talking about earlier. And then this section here is actually where the molding happens, right? So when we're looking at the predictive insights and really focusing on those pieces, we've got 3 that we're going to focus on, and really 4, because the feed screws also have an application with screw tips. So we'll look today at heater bands, we'll look today at feed screws and tips, and we'll also talk about some of the hydraulic pump work that we've done. So the heater band, as I said, sits on the barrel, and the barrel actually transports that plastic, and as it goes down the hopper in a pellet format, actually turns it into a liquid. So looking at these plots, we began to detect failures where we would see the energy of that heater band go south and cause a problem from a customer perspective. So what would happen is that would have a steady degradation as the energy was required to continue to move up to keep and maintain that heating perspective. And that was something that began to give us the early insights that there might be something from a predictive perspective that we could define for heater bands. So we built some dashboards around that as well, and we've been delivering that into the Millicron CRM so that they can take those failed heater bands and turn those into specific part orders from a customer perspective. So as Spencer mentioned earlier, we've been working with Orbis, and Orbis is a company that has many Millicron machines. But what we found in this process, as Spencer mentioned, is that they've saved thousands of kilowatts of hours of energy. So when you have a heater band that's failed, they're typically in a zone of 3, 4, 5, 6 heater bands. And you have a failed heater band on one side and 2 on the other side that are working properly, but they're working at a higher energy rate. And at that point, they're pulling in their max wattage and max amps to keep that zone in the middle that's failed actually operating. So we found that the energy consumption that was going into that on this part that's $200, $300, $400 is actually consuming thousands of kilowatts of energy. And the ability was not only to save that from a sustainability perspective, from an energy perspective, but to get their quality process improved from the heater band perspective as well. So screw efficiency. So screws, Stefan mentioned some early details on screws, and these feed screws, as you can see here, they're all they have processes that they allow the granules to fall in, and then they transfer down the screw as they move down the path. So we're looking at an efficiency algorithm where we can look at that screw continue to degrade over time, and based on the order and replace curve, we can address this in a proper process for the customer. But the idea of delivering this efficiency score gives them an understanding of matching that with their quality, with their cost per cycle, and the different details associated with that to make an informed decision on when they need to replace that screw. So we also have a screw tip, and this screw tip, so those screw tips in the upper corner, they sit on the end of the screw, and when that plastic moves forward, the tip is actually what's pushing it through the barrel into the mold itself. So what we were able to observe here, which was really very interesting, is looking at this time to pressure over a very short period of time, right? So these shots, in most cases, right, the cycle time on a shot is sometimes as fast as 3 or 4 seconds. Sometimes it could be 4 or 5 minutes. And then being able to look at that, how that curve began. So right, you see that shot, push it in, and it gradually fills and slows as the part fills as well. So we were able to see that, and then by looking at that algorithm over time, we're able to understand if there's a problem with that screw tip and if there's a failure that's occurring through that fill case of the screw. So we were also able to detect real-world hydraulic pump failures. So this is a great chart because it really shows the symphony in action and detecting those pump failures over time. And what you can see here in this first graph is really 2 injection cycles. So you've got two clear examples of what the normal injection cycle at that point looked at. And the Symphony is grabbing a 3-minute burst of data every 15 minutes. And you can see on July 10th, we have a change in amplitude at 12,000 hertz and also have some background noise that's happening. You can also see that the customer has also changed their mold, right? So their cycle itself has also changed from this broader cycle time, a longer cycle time, to a shorter cycle time in this same example. So there are a lot of folks that typically in those maintenance world will look at the heat output of that pump and begin to detect if there's a heat change. But we found that's really a lagging indicator to that pump performance and the failure that then occurs from that perspective. So if they're detecting a heat problem, then that pump has already gone to a point where it's probably not going to be able to be refurbished, and it'll have to be fully replaced and turned back around. So this was an important next step from a hydraulic perspective to understand these failures and utilizing the Symphony in that format. So we think that there are 6 steps in this path to predictive, and we're certainly with a lot of customers on that first step of connecting those machines. So from that perspective, you're monitoring the data, understanding the downtimes, looking at the different KPIs that are happening, and then being able to utilize the data science team, the artists that Stefan was talking about earlier, to really break through and chisel through some of the data and understand exactly what's happening on that machine and come up with these very simple solutions that can change an aftermarket business in a very short period of time. So it's really excited. I'm sad that Eddie wasn't able to join me today, but the work that we're doing with Millicron is very interesting and certainly has a great path to their continued success from an aftermarket perspective. So.